I'm looking forward to introduce to you this very interesting new instrument called ion mobility spectrometer. It's combined with a gas chromatograph, and it offers us really the possibility to find traces of volatiles in a gaseous environment. So where is this instrument produced or has been invented? It's company G.A.S. Analytical Solutions. Is in Dortmund. Formerly it was the Leibniz Institute, so it comes from a very university technical background. And so you have the facilities still in Dortmund at the biomedical center. So still university atmosphere, and people can exchange with each other. The company itself is very multidisciplinary. As you can imagine, such instruments to be built, you need somebody who is constructing, somebody who is producing, you need electronical engineers, you need software programmers, and last but not least, you need analytical specialists who can do something at the cutting edge, which currently is possible. So today we are happy to say that over 200 of those instruments have been introduced globally, installed, and are working. And even in last fall, G.A.S. Dortmund became a value-added reseller of the Agilent group. That means we can build in an OEM IMS module into their micro GC. As Sarah just pointed out, we have different setups for different requirements. This is a more mobile setup for detection of the VOCs in the gas environment. Here we have a medical setup. You can actually breathe into that manifold, and through a bypass the instrument takes the volatiles in. And you will see up in the lab set up the FlavourSpec instrument, which we recommend for food and flavor applications. So where you want to do several samples under similar conditions. And the secret is, of course, the Combi Pulse sampler, which prepares the headspace of each sample in a very consistent way. If we look more like in the chemical environment, you can think of any type of food, beverage product. It is about a flavor documentation. Think of today that you can take of each person on the world the fingerprint, and it is a unique identifier. We can get a digital fingerprint of the volatiles above each food product. And of course, this is totally different from product to product. But if it is coming from a certain environment, from a certain habitat, it also will lead to the identical fingerprint. So this is a new way of flavor documentation. Also, when you have products which have a deteriorated scent, that means you can find out first what is the difference in the volatiles, and you can dig in and find, hopefully, the contaminant. This is the industrial environment. You can think of monitoring volatiles in an employee's environment in the plant. When it gets dangerous, there will be an alarm. You can think of siloxanes in natural gas, which pollute and destroy the generators when you burn it and want to make power out of that. The medical area, we would like to help doctors to diagnose an intoxication in a very fast way without taking blood. You can think of different diseases which infect the lungs or which have markers. It's known, for instance, cancer has certain biomarkers. These are the topics. That's the secret or the heart of the ion mobility spectrometer. This so-called drift tube. You see how short it is. It's like shorter than a pen. And inside there is just a very high polished surface. No contamination should occur. And we can apply a high electric field. In front of is an ionization source, a tritium source, which produces free electrons. And there is a detector and an amplifier to it. So at the end of the day, we ionize the analyte molecules and we accelerate them in the electric field and we detect what arrives. The sketch is like that. We have the sample inlet here and this ionization chamber. There is a shutter, and upon an electronic impact we can open the shutter. The ionized molecules will be accelerated into the drift chamber, and we have here a so-called drift gas, nitrogen, which comes in. It's a countercurrent, and the molecules have to run against those nitrogen molecules. So depending on their size, on their volume, and on their mass, they will be slowed down. You can imagine people who want to go into a train and some people who want to go out. It's always the fast and the small ones, they are the fastest to go through. And this happens here. So first a little bit of ion chemistry. We have the sample which is neutral. We have a reactant ion which is H3O+. And we produce a cluster ion which at the end is the one which is accelerated. And so here you see the small ions, the red ones, faster already at the beginning, and throughout the separation in the IMS drift tube you will see this drift time resolution. The molecules become bigger and bigger, and this drift time is very characteristic, a unique molecular identifier. And we have to imagine that this is occurring in milliseconds. So several spectra can be measured per second. That gives a very, very fast measurement, a high resolution. We can go into very details about calculating the drift constant, which is the relevant parameter. So you see again the reduced mass, the ion charge. Also important is this drift gas density. So if we have the machine somewhere in Ecuador at 3,000 meters altitude, it's different because the atmospheric pressure is lower than here at sea level. This is the main information which we can see from an ion mobility spectrum. This is the so-called reaction ion peak. So this should be always present. It shows you also about the purity of the instrument. And here we have an analyte which is hexanon. You see a monomer peak. That means one analyte molecule shares one proton. And it can be that two analyte molecules share a proton between each other. It's a bigger cluster. In some cases we even observe trimers. The important thing is that especially the dimer peak is very sensitive to quantity, so we can quantify. The position is the qualitative mark, and we often choose the reaction ion peak as the reference at 1, and everything which is longer drift times will have a higher ratio above 1. Faster molecules, like for instance H.A.S. or ammonia, they would appear slightly before the reactant ion peak. This is for physical chemistry specialists. You can do a lot of work about ion chemistry in the gas phase. It's very complicated per se, but you will see that using this type of spectrometer we get very fast, very pertinent information, a so-called fingerprint. The sensitivity of the instrument depends, of course, on the ionization possibility, so the so-called proton affinity. Maybe you can think of the ion mobility spectrometry which is used at the airport. We can get sometimes a random screen, and they touch our belt, they touch our the notepad keyboard or the handbag. That means on those traces they can find drugs, they can find plastic explosives and narcotics. So a very fast test. Usually you don't need to wait 30 seconds. It's already cleared to go. And this is for a very simple testing. If we have a food matrix, our matrix releases a complex volatile mixture, and we could have a lot of ion competition. That's why we have the pre-separation by the gas chromatograph in front. So you can have an ordinary gas chromatography column. Here in our case we have a short column to allow faster measurement times. We don't need a perfect GC separation, but of course the better we separate here, the easier it will be to interpret the ion mobility spectrum. It gives us a two-dimensional representation. Could be the Tasmanian Alps. Here we have the reactant ion peak. As soon as there are analyte molecules, they take some of those reactant ions and are protonized themselves. And the position in the IMS spectrum is very relevant, as well as this position. This is depending on the GC retention time, or the so-called Kovacs index, the retention index. To look at the data later on, I will show you upstairs. We can, in a very easy way, in a very proprietary and sophisticated data analysis tool, we call it the Vocal, we can look at these three-dimensional data. You can look at details, you can have different type of representations. It is also possible, if you have a very dedicated application, to reduce the software to do just one job which you want. For instance, we have an application for the beer industry which allows to look at the end of fermentation cycle. When we do the fermentation of beer, we ferment the sugars into alcohol, but there are also some byproducts formed. I will show you later how this looks like. And so there we only need to look at two peaks, pentanedione and diacetyl, and if they are in high concentrations, the beer is contaminated, not nice, and we need to wait longer until the yeast has fully digested those products, and we come down to a lower level, and then the beer is pleasant to drink. So we can look at only such two markers, and the rest the technician doesn't need to know. So very universal in that sense. And if we look at the data itself, we have very often a projection of the peak down to one plane. So we have here the retention time, the measurement in seconds, and here we have the mobility, and you see the reactant ion peak as a red mark. This means a high peak intensity in millivolts expressed usually, and we can think of that this is a high peak here, and these are small peaks here. Now we can handle the measurements here in this browser, and we can add relevant measurements in a so-called project measurement window. It's all targeted to be able to compare samples between each other. We can, for instance, look at the peaks themselves, make the quantification out of those peak heights. We can produce a calibration curve. This is geosmin, for instance, a contaminant in drinking water, and we can find a range here from the different concentrations. You see this is in nanograms per liter. Now, if we look at the so-called test mix, which we use often to verify how our instrument is working, we often use a series of ketones from butanone to nonanone, sometimes also decanal on top. And we can mark the regions of those molecules in the spectrum. The more we know, I will also show how we can identify molecules. We can visually see where a molecule is, and it allows us, the software, to draw such kind of rectangles here. And there is a software tool which we call the gallery plot. It will display those regions next to each other, and you see the test mix has these 6 peaks now. And you see they are all present. If we have a series of concentrations, this type of representations leads us immediately and visually to the fact that peaks are increasing with concentration. So this is the lowest concentration, and you see that from here to here, the heat map itself shows already peaks which are much lighter in red, and here it is more pertinent and more easy to interpret. So in some cases, this type of representation will lead us to possibilities to classify, good or bad, if one peak is present, which is the contamination. If it is that simple, then based on one of those gallery regions here, we can say yes or no. If we want to do this molecular identification, we have the big basis of retention indices from the NIST GC retention indices database. For each type of column, retention indices are published, sometimes from 200 labs, sometimes only from a single measurement. But you get those, and the thing is, what we need to do, we now know our molecular positions, and we match the retention time and lock it with the retention index. We call it, it's a GC column normalization. At the end of the day, similar retention indices will appear, will elude at a similar retention time. And we can start to identify unknown molecules, which at the end of an identification exercise, you would use your sample, you would spike it with the reference material and see, yes, it is there. So there is no other way to go around identifying unknowns within the odor and volatiles is a complicated task anyway, so I don't want to make an illusion. It will stay a difficult task, and most probably you will also need other analytical techniques to confirm. But I think this is normal analytical life. What I can propose with this FlavourSpec instrument is, like our cameraman here, we make a snapshot of the volatiles. So if we have a cup of tea or a cup of coffee, sometimes we see this kind of fume coming up, but this is not the odor yet. This is only water vapor carrying some of the volatiles. And it's actually very difficult to see odors. It's impossible for our eyes. We cannot see them. We can only smell them. But here we make a picture of the odors in 2 dimensions in terms of retention, separation in the GC, and in terms of drift time in the ion mobility. This is done within a few minutes, and we get that fingerprint of the volatiles. And this fingerprint can be used to do different tasks in the food area, food environment. It can be used in quality control, or we can look at maybe different rices, and if one is called a basmati rice and the other one is called a jasmine rice, we can look at the volatile patterns, and we will find very unique molecules which make up this type of note. If we talk about very complex volatile mixtures which are released from tea or from coffee or from tobacco, this type of headspace is very complex, but it will tell us what type of tea, how it was aged, where it did come from which region, and that's how we can differentiate different Chinese green teas or whatever you could think of. Also possible in these beverages from China, like the different baijus or Huangjus, this yellow wine or white wine, we see very characteristic fingerprints from different regions, and it is possible to differentiate. In terms of soy sauces, we can think of that. We can differentiate different types of products. And also the authentication of food. Sometimes we buy orange juice and it says fresh orange juice, could imply that it has been freshly squeezed and non-treated at all. If we do the verification and we find linalool in this headspace, we know it is processed. So a famous publication says that after heat processing the orange juice, we can form linalool. It will never be present in the fresh fruit. So we can make a test, and it will be very easy to see the difference. Also, other products are very sensitive to certain food fraud. We have topics today, very hot topics in Italy about olive oil authentication. Is it virgin olive oil? Is it extra virgin? Is it Lampati? Is it a fake product blended with cheap raw materials? We can get the identification out of that. So this is how the instrument is supposed to work, and you will see it working upstairs in a moment. We have as a key component the headspace preparation in the sample vials. There is a so-called agitator which can produce a consistent temperature, and you can put your sample for a certain time in there. It is all possible to be programmed through this controller. And at the end of this preparation, the robot will take a bit of the headspace sample and inject it in this injector port. That's an early publication of a Spanish professor saying that this technology can not only look back what has happened with your product, but it can be used also in what is going to happen to your product. So aging phenomena, if a product is going to deteriorate, you will see it already in advance, watching certain markers. So that's quite interesting. Many times in analytical science we can only look backwards. Yes, it happened, but it's difficult to make a prediction model. Where would we place GC-IMS? So many people immediately start to compare this instrument with the high-end GC mass spectrometers, and we have to acknowledge that this technology has been evolving over the last 30 to 40 years. People have started to build huge libraries, and some are really experts since 10, 20 years, looking at the mass spectrum and can already see what is wrong or what is good. We don't want to directly compare it with that, because this is probably the golden standard for the next years still, how we kind of try to make a molecular identification. It is possible to combine such instrumentation with the GC olfactometry port, so we can put our nose there and smell what is the molecule which is currently analyzed by the mass spectrometer. So this combination we don't want to replace, but it is a complementary, a kind of a in-between solution. When we smell on a product and we know that our wine has a cork taint, we smell that within milliseconds. And then we know, I don't like this wine because there is the cork taint in it. We do quite some work until we can prove that with this type of instrument. We will be able to do some kind of fast analysis with this GC-IMS as soon as the volatile compounds composition changes, our digital fingerprint will show up differences. And we can look at that after like 15-20 minutes measurement time. So this is very easy to use, straightforward. It is fairly totally consistent compared to electronic noses, which 10 years, 20 years appeared with metal oxide sensors. These sensors were drifting all over the time. Every couple of weeks you had to replace the database, rebuild it. Ion mobility spectrometry has always this drift constant as a very precise measurement. So you can build up fingerprint databases and so on, and it is a very attractive value for money compared to such a huge investment. This is the workflow, how we do it. So we got this morning a couple of samples and they are already measuring in the GC-IMS. We fill it. We don't need to fill the full vial, just maybe 1-2 grams. And then we generate the headspace. So this is done automatically. We can define the parameters, 5 minutes, 10 minutes, half an hour, set the temperature, and then the sampling is happening. It's just within a few seconds, the headspace is taken and transferred into the FlavourSpec instrument, and we can start with the data analysis. So again, the scenario of having a detector here, flame ionization detector or the mass spectrometry, we will always have in complex mixtures this type of situation that peaks are overlapping. And that means either we make the measurement time even longer or we change column. That's the method development which can help here. It's well developed, it's well known, but there is also a kind of limitation to the sensitivity or a complexity because of overlays. In the IMS, we have a secondary dimension, and you see that a complex peak then will have multiple small peaks, and they can belong to isomers or can belong to a different molecule. So with the secondary dimension, some people make GC-GC or MS-MS and so on, hyphenated technologies. You, in most cases, need a PhD or more experienced person to make a meaningful data interpretation. Again, here we can compare the fingerprints as first sight, see is it different between good and bad, and so on. So in the case of beer industry, what I just told, the VDK determination, these vicinal ketones, pentanedione and diacetyl, we have the possibility to analyze them in a very unique mode. We can switch between positive and negative ions very fast. So in this case, we eliminate all the volatile compounds from the beer matrix if we detect in the negative mode, and we only are sensitive for the 2 target molecules. We can calibrate this, and then it is possible to set the limit of approval when the beer is good to get into the barrel. If we talk about the case of dairy products, UHT is a technology to make the milk more lasting on the shelf, but still it is not forever. It's still aging, and you see that after a certain time, after like 2-3 weeks, we get molecules building up. Some are always present, and these are often aldehydes which come from the fatty acid degradation, the byproducts which give us a nasty contamination note. It is rancid smelling, and we can visualize this here in a very smart way. Last year I was installing a FlavourSpec instrument in New Zealand, and within 1 year now this analytical specialist with his PhD student have built up a big database of Sauvignon Blanc, and that's their major product there. And you see they have an aging profile, and certain volatiles will increase over time and others will decrease over time. So you have, with this possibility, Frank Benswitz from Constellation Brands showed a poster at the WineTech conference last week, and we can really see that you can build up an aging model for the wine. And there are very special molecules, he is starting to identify them now, which are unique identicators. And if you look at only a few, 6, 7 molecules, you get a perfect aging model. And other things are made with wine, like from which farmland origin is it coming from. We can also look at the grapes. Are they good quality grapes, or are they already fouling? Do they have these brown spots at the skin which will exhibit off notes during the fermentation? So a new tool for the wine industry yet to be explored. And here is an application where we look at packaging materials, and here a packaging material which is heavily outgassing. So this can go to the food product. Food contact materials could be checked with this instrument, and it is very fast to see whether a product is good or not. If we would like to benchmark, I don't want to go through all those points, but maybe the major point is the size of the instrument. Relatively easy to put it up. I heard this morning already comments, oh, it's so small. And if you compare it to the G.A.S. technology, you will need vacuum pumps, you need helium installation. So all these peripherals are very heavy. In that sense, even the FlavourSpec instrument, you could put in a minivan, put it from location to location. We could run it from a gas bottle and from a car battery. That's possible. We have been demonstrating this already. So robust, but ppb sensitivity towards the key analytes in volatile analysis, namely to those where we are sensitive as human beings, those molecules with a lot of functional groups which are easy to be ionized. And these are the typical examples. So process control, for instance, in the bottling lines, you can actually monitor between the different products, is it now clean or not? The product authentication, even the high distillates. We have another module for avoiding the contamination with alcohol itself, so you can discriminate whether it's methanol inside or not, or if those high-priced distillates have been frauded, just added some extra alcohol. Things like that are possible. You are doing sensory analysis here, and you will have the cases where the sensory panel is confused when the samples are too similar. So in fact, either you make a more discriminative test, you prepare new samples, or you look if this is true or if we have a consistency between the samples and people cannot find it out. Then, of course, depending on the samples, you need to find out different strategies. But we have seen many occasions, one of my customers was asked, can we differentiate, can we measure? But depending on how we use the product, it can be just after application or at the end of the application, we will see differences. Say, if you talk about deodorants in the fragrance industry, is it still there, a certain signature of the deodorant after 24 hours is one of the big questions. And if we can find it and the sensory panel cannot find it, then yeah, we have to develop the fragrance in a different way. But it can support this kind of flavor and fragrance developments. Quality control, again, if possible, we find the cases where we can classify, and then we can say yes or no, or it's that group, it's this group. Or if we talk about the Manuka honey, we can say this is the original, it has the original fingerprint, and this is a fake product coming from elsewhere. So we separate by GC, and we have an additional separation at the sensitive detector itself. And so we can really go towards QC laboratory use, or we can do like from product to product, develop new methods. So another configuration is this so-called FlavourSpec instrument. Very early use has been done already in Dortmund. Some people from the medical sector were interested, and in that context it became more and more important to be able to move the instrument to the patient, because some people are using PTR-MS technology. If you see this machine, it's a big cupboard filling like 2 square meters, and you cannot move that instrument to a patient. And especially working with children, for instance, it's intimidating if you have to sit in front of such a big analytical equipment. This is very easy to use. We can actually roll it to the patient, make the measurement, and take it away. This is Daniel Sanders, one of the analytical specialists in Dortmund. And he shows that we can use either the way of blowing directly and taking through the bypass the sample, or you can be totally offline and you take a patient to blow through a tube, and you take with a disposable syringe the headspace and put it into the machine via this small adapter. As an example, you see him, he was a heavy smoker, and after smoking a cigarette, the headspace of his breath looks like that. And this is after a few days of abstinence, non-smoking, and this actually made him switch to vaping technologies, not normal smoking anymore. But it just gives you an idea of how sensitive the machine is, and that all these molecules mean something. So we can find alcoholic poisoning, especially in the Asian, Southeast Asian environment. People buy cheap spirits and they get often contaminated by methanol. So it's straightforward to identify in a hospital emergency, is it that or is it another problem? It's also used in a toxic triage project. That means a big funded European project looks at intoxication discovery after a catastrophe event. Say if somebody puts a small sarin dose into a metro and a lot of people get symptoms of intoxication, you should know who is really suffering of the nerve gas intoxication or who has another problem. And so emergency people can use that instrument in that context. And of course, other medical applications. The generic instrument is this, the small box which you will see above. And it is possible to use here not an injector, but a so-called 6-port valve. We have a sample loop, and there is a pump which is constantly aspiring the sample and puts it through the sample loop. When we are ready, when we have conditioned the sample loop, we can say inject, and this 6-port valve is switching the position and puts the whole sample loop via the carrier gas into the separation column and into the IMS. This is the schematics of the instrument. And it can be customized, so it can be also equipped with this circular gas flow unit. That means it is a setup of a pump, a compressor, and different molecular sieves and active carbon filters. So it takes in the ambient air, purifies it, and circulates it at the end between the machine and this unit. So if we inject a tiny little trace of sample, it will be purified again with these active carbon filters. And like that, this instrument becomes gas bottle or gas installation independent. It's very easy to put it in a minivan and just power it via the car battery. These are some of the ideas of how this instrument as a process control or as a work environment control can be used. Toxic ingredient compound monitoring or the quantification of the gas supply in the gas grid. We cannot smell propane or butane. That's simply odorless for us. So we add the sulfur compounds that we can smell gas in case of a leak. You can think of the siloxane determination, a very complicated analytical task. The machine is suitable to do that, is then calibrated in a very sensitive way. Propellant gas can be contaminated and affect the quality of a lot of fragranced products. And even the sampling bags can be contaminated and outgas. So this is just some applications. And if we want to fully automate it, you can think of that this instrument is measuring, and the results, the quantification results, can be transmitted via a communication directly into a control room, or they can produce in the factory an alarm. So it can be as sophisticated as that and as automated as that. This is a petrochemical example. A BTEX determination is always a task which has to be performed. And you see here the sensitivity in the ppb range. We can have very low significant detection, 10 ppb of benzene. And this is a toxic ingredient like dimethyl sulfate. A big chemistry maintenance company called Bilfinger has asked about this monitoring, process monitoring, and we can show on the screen of the instrument after a measurement cycle how many ppbs of dimethyl sulfate is in the air present. We cannot smell that. We can smell it at higher concentrations, but then we are already in danger as human beings. And dimethyl sulfate is a very common, highly used methylation agent. So these are typical applications where it is very useful for the working in safety environment. And Bilfinger is including that in their control setup of various other parameters. In the gas odorization environment, we like to measure hydrogen sulfide and COS. It's integrated in the Agilent Micro GC, just another possibility. And here we have nitric oxide in ethane, and one of the very interesting things is that we don't have any hysteresis, so we can come from higher concentrations down to almost zero, and we can come from zero, no measurement, up to the same level, so no hysteresis. Many of those chemical detectors will have a hysteresis of what has been measured before. So various possibilities to get the air samples from. They can be sampled here as a continuous monitoring and can be transmitted into the control room as an alarm signal, or you can do the data analysis as introduced before to see what is present, what is not present. One thing is about the siloxane environment to get clean natural gas for burning. If it is containing siloxanes, it will destroy the generators. And so they would like to use the very expensive active carbon filter up to the end. And you can measure at this end here when the filter is breaking through, and then you need to really change it. So these are pictures from factory environment in the Netherlands. And this was a project in Madrid where I was myself present. It's about the odors emitted from the waste treatment plants in the outskirts of Madrid. They have different factories, like the landfills, the sorting plants, the biogas plant, and even drying plants. So it's very complex, and each factory should actually take care of not emitting nuisance molecules in the air, but sometimes they are working in the Spanish way, so they don't care. And they blame the neighbor factory for emitting the nuisance molecules. They can say, this is the wastewater treatment from there. This is not my factory. We had the task to determine fingerprints of the volatiles, and we could go to the stack, measure it there, and then go into the plume, into how it is with the wind direction emitted into the environment, and prove that certain fingerprints were again present there. So that was a pioneering activity. We equipped this Renault Kangoo with a truck battery of 24 volts, and we could use that during 2 days. And so this is how mobile the instrument can be. Also today, in a changing legislation environment, the Chinese car manufacturing industry is putting now a big handle on the volatile emissions within the car interior. So they, compared to previous norms, the German car industry norms were smelling with panels, like 20 trained people were smelling the leather pieces, the carpet pieces, the wood pieces which are built in the car, and were approving or disproving according to well-established sensory norms. Now the Chinese industry comes and tells us about 12 molecules which have to be below certain defined thresholds. And these are the molecules, and these are the requested limits. And our instrument, for instance, can then be equipped with a pre-concentration unit, a thermodesorption unit, and we can get to those limits and offer this type of measurement. So you see this gallery plot again with the different type of molecules and the detected levels. Within a 15-minute cycle, everything optimized, we can do this kind of car interior testing with the GC-IMS. And this is an example about really identified outgassing from the beverage bottle industry. We can measure acetaldehyde and detect it at the significant quantities which will endanger or contaminate the beverages. So these are various applications here in process control, personal care, in environmental monitoring. This list can grow, and of course, if there is a potential of not just building one instrument, it will be more interesting for G.A.S. Dortmund to really fine-tune everything, the firmware on the instrument, to the application, evaluation of the data. And otherwise, it is an open system, as I can show you now, where we have all possibilities, all freedom to interpret the data and to prepare the method. This is a possibility to integrate a module to the high-end GC, like an Agilent or Shimatsu. Then you have also the liquid injection, and those people who are interested in monitoring pesticides, at the moment this could be the most interesting setup together, because there we can get the non-volatile or semi-volatile compounds into the gas phase, and at the end into the GC-IMS. And this is a way how it was integrated into the Agilent Micro GC. And thank you for your attention.